Good afternoon, all of you.
Good afternoon, sir.
What was the last thing we covered in the previous class?
Good afternoon, sir.
Satellite velocity.
Orbital velocity.
Orbital velocity.
Root here. Okay. Did we calculate the field inside a cavity?
Yes.
Yes, sir.
Yes, sir.
You mean this we have done?
Yes, sir.
Yes.
Yes, sir.
Yes. Start escape velocity. Am I right? Yeah.
Sir, just a question. So, how many more lectures do we have of gravitation now?
2 more maximum
After today.
after today.
Sir, after this electrostatics, right?
Yeah.
Sir, after the chapter finishes, can you take a doubt lecture
Yeah.
for all the doubts? Thank you, sir.
No. How do you define escape velocity? The velocity with which a body should be thrown so that it escapes from Earth's gravity. Minimum velocity with which a body should be thrown so that it escapes from Earth's gravity. If I throw a body in the upward direction, how much velocity should I give so that it touches the ceiling? I'll conserve the total mechanical energy here and there, right? So total mechanical energy initial is half m UE square minus G capital M small m by R. Half m UE square minus G capital M small m by R. This is the potential energy. This is the kinetic energy on the surface of Earth. Agreed?
Yes, sir.
Yes, sir.
Yes.
Total mechanical energy final, kinetic energy plus potential energy. You are sending this mass to a point of no comeback. It should not come back. That means there should be no force of attraction between the two. That means the potential energy should be zero.
Yes, sir.
Yes, sir.
Kinetic energy should be zero because you are asking for minimum U. UE minimum. It should just reach that point of no comeback. That means kinetic energy at that final point should be zero.
Yes, sir.
Now equating the total mechanical energy, half m UE square minus G capital M small m by R is zero. UE is root over of 2gm by R. Root over of 2gr square by R. Root over of 2gr. Right? UE is root over of 2gr. Escape velocity is root 2 times V0. V0 was orbital velocity. How much was orbital velocity? Under root gr. So escape velocity will be root 2 times orbital velocity. On the surface of Earth, escape velocity will be 11.2 kilometers per second. On the surface of Earth, escape velocity will be 11.2 kilometers per second. Right? Generally committed mistake by the students is they make it 11.2 kilometers per hour. It's a blunder. 11.2 kilometers per second. Kilometers per hour is a much lesser value. Kilometers per second is a very abnormally high value. You can reach Delhi from Mumbai in 2 minutes at this speed. So this is the minimum velocity I should give so that the particle escapes from Earth's gravity. Because it escapes from Earth's gravity, potential energy is zero. It is minimum kinetic energy, so the kinetic energy at the final point should be zero. It should just reach that point. So you equated both the energies and you found out the escape velocity. How do you define escape velocity? Minimum velocity required for the particle to escape from Earth's gravity. Minimum velocity required. Minimum velocity required to escape from Earth's gravity is defined as escape velocity. It will be root 2 times orbital velocity. It will be root 2 times orbital velocity. Right? One more important point. Some students ask, when you see a satellite or a probe towards Mars, Jupiter being launched, you don't launch it at 11.2 kilometers per second. Hardly the velocity will be 2 kilometers per second. Because this is the total energy you are giving in one go. It's like telling you, I want the marker to touch the ceiling. There are two ways. One, throw it with certain velocity. Second, keep moving it upwards towards the ceiling and I can move it at any speed.
Yes, sir.
Now here minimum speed does not make sense. When does minimum speed make sense? When you throw it with certain velocity so that it goes and touches the ceiling. When you give whole of the energy in one go, it will be 11.2 kilometers per second. A space shuttle will have an exhaust. There is continuous supply of energy. You can make it rise with any speed of your choice. Right? If you give whole of the velocity in one go, then it will be 11.2 kilometers per second. Do you get that point clear?
Yes, sir.
Sir,
Hmm?
this 11.2 is escape velocity from Earth's surface, no? Right, sir?
Right.
Else it will be root to V naught, no? From any other point.
Now V naught is the orbital velocity close to the Earth's surface. Now, all of you listen. This point is a very valid point. All of you listen. This escape velocity is from the surface of Earth. Orbital velocity is close to the surface of Earth. Only close to the surface of Earth you will get under root gr. Suppose if you take orbital velocity at some height h, यहाँ orbital velocity v naught, then escape velocity from here is related by this relation. Whichever orbit you take orbital velocity, from there the escape velocity will be related by this relation. Now escape velocity here will be root 2 times v naught. If I take it on the surface of Earth, orbital velocity is close to the surface of Earth. If you take one of them at a height of h, both of them are at one particular height of h. Somebody is asking, does it depend on the direction? Energy doesn't have a direction. Energy is a scalar. Only thing, if you
So-
take Earth's rotation into consideration, then the velocity you give in the direction of Earth's rotation, opposite to the direction of Earth's rotation, will be different. Because you should add both of them.
Sir, I didn't understand why we took the total energy, the final total energy, the kinetic energy and potential energy as zero. Does
You
the
are
body
sending it to a place where it is not coming back again. So there is no force of attraction there. If there is no force of attraction, what will the potential energy be?
zero?
Now you are sending it with minimum velocity from the surface of Earth. That means it should just reach that point.
Yes.
If it just reaches that point, what should be the kinetic energy?
Oh, sir, got it. Zero, sir. Got it. Thank you.
Right.
Noted, sir.
Noted, sir.
Okay. Okay.
Sir, I had a doubt. So, is it possible to give so much velocity at once?
It is. It is. It is quite high. But the problem is when you give so much velocity, the body gets burnt out before leaving the Earth's atmosphere. When the velocity is quite high, air friction will generate enormous heat. So the body gets burnt out before it goes out of the Earth's atmosphere. Hypothetically, did you people see the movie Superman Part 1? Superman Part 1 देखा है आप लोगों ने?
Yes, sir.
Yes, sir.
We try to show you Superman.
Don't bother with these, huh? I'll take them in with the other equipment.
Thank you, Clark.
Sure.
Listen, a whole bunch of us are going up to Mary Ellen's, play some records. Would you like to come?
Sure. Sounds like it'd be a lot of fun.
Ken can't make it. They got a lot of work to do.
What are you talking about? I just finished stacking all the...
All that?
Oh.
Oh, Brad. Come on, Lon.
Come on, let's go. Come on, he's got to...
Now this guy is the Superman. That this guy. Watch this scene. Right? He kicked the ball with a velocity of
11.2.
not less than 11.2 kilometers per second. The ball doesn't come back.
Is this a very old movie?
Superman's, there are 3 series. This was part 1. If I'm right, 1989 or 87.
So 1978.
1978. Perfect. But we saw that in 1985 or 86, if I'm right. Now, suppose you take this projected with a velocity of u. This is projected with a velocity of u. ue by 2. Half the escape velocity, then it will not escape from Earth's gravity.
Yes, sir.
It will not escape from Earth's gravity. They are asking you to what height will the body rise? Find h. Will you try or should I just?
We'll try.
We'll try, sir.
I am waiting. They have projected the body with a velocity equal to ue by 2. Half the escape velocity.
So for all these problems, you have to neglect rotation of Earth, right?
Yeah. This result is the net velocity. If I am finding it tangential, velocity with respect to the surface plus velocity of the surface with respect to the center will be velocity of the body with respect to center. So this is the net velocity with which you are finding.
So H is equal to R by 3.
R by 3 is correct. Yes. All you have to do is conserve energy between the 2 points. What is the total mechanical energy initial? Half m UE square. UE square is root over of 2gr whole square minus g capital M small m by r should be equal to kinetic energy here is 0 minus g capital M small m by r plus h. I call it small. You need to calculate h. You can write r plus h, no issue. Small m gets cancelled out. This is 4 and 2. 4 and 2, this will be 8. Root over square root will go 2gr by 8 minus gr square by r minus gr square by r plus. This will become 4, 1 r will go.
So cancel GR also.
Yeah.
1 r has gone, g will go, 1 r will go. This is 1 by 4 minus 1 is equal to r by r plus h with a negative sign. R square में 1 r has gone, 1 r has gone with this. Here 1 r will be left. This will be minus 3 by 4 is r by r plus h with a negative sign. Just cross multiply and simplify, you get the value of capital H. Height to which the body rises. No big deal, it is just conservation of total mechanical energy.
So H is R by
H is R by 3, yes. Now, this is what JEE people did to this problem. They have dug a tunnel to a depth of H. Point mass of small m is fired with a velocity of u. They ask the height to which small m rises. U is lesser than escape velocity. Less than escape velocity. Will not escape from Earth's gravity. Height to which it rises. Now, technically, what should you do? You should conserve total mechanical energy at these two places. Total mechanical energy initial is equal to total mechanical energy final. As simple as it. For 2 marks, it's a valid question, but they asked only for 2 marks. Where they caught many of the students off guard is kinetic energy is half mu square. You don't have an issue with that. Potential energy here is potential due to Earth into mass. Here kinetic energy will be 0. Potential energy is minus g capital M small m by r plus h. They gave you the height h. They're asking you the height h. They gave you u. Simplifying this is a child's play for anyone, provided they remember the expression for potential inside a solid sphere. Without turning the pages, can any one of you tell me the expression for potential inside a solid sphere?
Minus gm by 2 r, 3 r, 3 capital R square minus.
Small r.
Small r.
Small r.
Small r.
Here, what is small r?
R
R
minus.
minus H.
Don't carry a negative sign again here. You already carried it here. Now, people who remembered this expression, 2 marks, worth it. They finished the problem. People who forgot this expression know what is to be done. They knew everything that has to be done. They don't remember the expression for 2 marks. They cannot sit and derive it. You understood how JEE people played with this? So remembering these expressions are a must. Did I summarize all the formulae for you on the board?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Do remember them. 2 mark के लिए they asked such type of questions. One equation and one variable. Capital H is to be calculated.
Sir, it is given that the hole is not very wide, right?
It is thin. A tunnel, thin tunnel.
Okay, sir.
If not, capital M mass of Earth will change and the expressions cannot be used. Solid
Yes.
sphere expressions cannot be used.
So the escape velocity inside the Earth will be different from the surface, right?
Naturally, yes.
Okay, sir.
Can I rub the board?
Yes, sir.
Yes, sir.
So do we have to calculate H in terms of the variables?
Right now, don't. It will be lengthy because I don't know the value of U. They have given some value of U, which you can.
Yes, sir. It's quite lengthy.
Yeah. Now listen. This is a star of radius 2a. A is astronomical unit. A is astronomical unit. This is a star. There is another star of radius A and mass M. A bigger star of radius 2a, a smaller star of radius A. Distance between the centers is 10a. A is astronomical unit. Till here is the question clear.
Yes, sir.
Yes, sir.
A point mass of M need to be fired in such a way such that it reaches the smaller star. Find U minimum for which small m reaches the smaller star. Find U minimum for which small m reaches the smaller star. Now here, small m is much lesser than capital M. Do not worry about the recoil of the stars. The stars do not move. Assume they are at rest. Solve the problem assuming that the stars are at rest.
That's why you have given m is very less than m, capital M.
Pardon?
So that's why you have given small m is very less than capital.
An old JE question. Think carefully and solve the problem. It is a very well constructed problem.
Sir, if small m and capital M were comparable, M would like draw the stars towards itself as well, right?
Yeah.
Okay, sir.
So 10A is the distance between the centers of the stars, right?
NA is distance between the two centers.
Sir, what's the answer?
Wait.
Okay, sir.
Can you give 2 minutes?
Yeah. I'll wait.
Done.
There are 2 points of a catch in this problem. First of all, decide the point where the field will be 0. Decide the point where the field will be 0. Somewhere in between the field will be 0. If small m crosses this point, it will by default be pulled into the smaller star. If small m falls short of this, it will come back to the bigger star. This is the first catch where 90% of them falter. If small m crosses this point, call this distance to be x. This will be 10a minus x. If small m crosses this point, it will by default be pulled into this. If not, it will come back. First, decide what that point is. G sin 16 capital M by x square is G times capital M by 10a minus x whole square. Is this thing even visible for you people? Are you people on mute?
No, sir.
No, sir.
No, sir.
Now you understand why they gave you 16m here. Cancelling out 4 times 10a minus x is equal to x. That is square root on both sides. 40a is equal to 5x, x is equal to 8a, x is equal to 8a, this will be 2a. This point is at a distance of 80 from here, where the field will be 0. If small m crosses this point, what is the net field here towards the right? What is the net field here towards the left? If small m crosses this point, it will by default be pulled into that particular star.
Yes, sir.
Now, total mechanical energy here, half mu square minus G16 capital M small m by 2a. This is the potential energy between the bigger star and smaller. Minus G16 m by 2a is the potential, that into small m will be the potential energy between the two. This is the second place where many students fall for this. They forget to take the potential energy between small m and capital. Sorry. They forget to take the potential energy between small m and capital M. Minus G, because of capital M, the distance is capital M by, from here till here it is 8a, 8a into small m. This is the total mechanical energy here. Obviously, there is potential energy between small m and capital M. This is kinetic energy of small m, potential energy between the two, potential energy between these two. Quite a few times students forget this. Now when the small m reaches here, kinetic energy will be 0. Potential energy between small m here and 16m minus G16m small m by this distance is 80. Minus G capital M small m by this distance is 2a. Once I know x is equal to 8a, solve this equation for you. The minimum velocity you should give so that it crosses this point. Once it crosses this point, it will by default go towards that particular star. That's why we never send any space probe straight towards that planet. From Earth, if you send a space probe towards Mars, you send it straight, it will go and collide with abnormally high speeds. After crossing this point, the space probe will accelerate towards this. It will acquire abnormally high speeds. Hence, they will first send it into an orbit. From this orbit, they will put it into the orbit of this. Slowly decrease the radius and make it land on that particular planet. You send it straight, it will collide with very high speeds.
Sir, sir, in this total mechanical energy initial, why it is GMM by 8 is it should be 10, you know?
Distance from this center till here is only 8. You are finding out the potential inhabit in small m and capital. For capital M, what is the potential here?
Yes, yes, sir. Thank you, thank you. I got it, got it.
So do we solve for?
We don't hear you. Jay Shankar, your voice is resounding.
Sir, I said that should we solve further?
Not required. If you understand the problem, I'm okay with it. Can I rub the board?
Yes, sir.
Yes, sir.
Total mechanical energy of a satellite in an orbit. This is mass capital M. Satellite is going with an orbital velocity v naught at a height of small h. So what will be the total mechanical energy? Half m v naught squared minus g capital M small m by r plus h. R is the radius of Earth, H is the height of that body from the Earth's surface. What is the orbital velocity? Root over of Gm by R plus H whole square minus G capital M small m by R. This turns out to be G capital M small m by 2 times R plus H minus G capital M small m by R plus H. Remember this. This is the expression for kinetic energy. This is the expression for potential energy. Minus G capital M small m by 2 times R plus H. Total mechanical energy. You have done something similar to this in Bohr's atomic model. Kinetic energy plus potential energy. There also, if you people remember, the value of kinetic energy and value of total mechanical energy are the same. There also, if you people remember, potential energy was 2 times kinetic energy.
Yes, sir.
Yes, sir.
Yes, sir.
And the negative sign is very important. Bohr's atomic model में first orbit when you see it is minus 13.6 electron volts. Second orbit minus 10.2 electron volts. Minus
Minus 3.4.
Minus 3.4.
3.4.
Then minus 1.15. Negative sign is very important. The negative sign tells you that it is a bound orbit. Total mechanical energy is negative, implies it's a bound orbit. What do you mean by bound orbit? Electron is bound to the nucleus or satellite is bound to the planet. It will be going around the planet. The moment the total mechanical energy becomes zero or positive, it is unbound. It is free to move. It will be a parabolic, hyperbolic, or a straight line. It will escape from Earth's gravity. Recollect, electron is in the first orbit. What is its energy? Minus 13.6. To remove the electron, I have to give plus 13.6 electron volts. Hence, this energy will be negative. When I give plus this quantity or more than this orbit, the satellite is lost from its orbit. So the negative sign is very important and significant. Till when the energy, total energy of the satellite is negative, it is bound to the planet. Let me write it in a simple expression. Total energy will be minus G capital M small m by small r. Small r is R plus H. What if the orbit's radius increases? What if the orbit's radius increases? Impulsively, students will say if R increases, energy decreases. Wrong. Because of the negative sign, if R increases, total mechanical energy also increases. If R decreases, total mechanical energy also decreases. Right? dE by dr. I have it 2 here, I forgot. dE by dr is minus G capital M small m by 2 minus 1 by R square. All that I did is differentiated with respect to R. Negative of negative is positive. dE by dr is G capital M small m by 2R square. This is positive. What is the significance of this positive? If R increases, energy also increases. If R decreases, energy also decreases. We will use this concept in 1 or 2 problems from Erdo in the next class. Remember this for them. Don't forget this.
Noted, sir.
Now listen. If you people carefully observe this, think logically. When I sit alone and think about all this sometimes, there is a chill that goes down my spine. It is so much beyond imagination. Consider this carefully. Kepler's laws were designed in the 15th and 16th century when Newton's laws were not yet born. He didn't know the reason for the force of attraction. Analyze logically, you will know the greatness of these people. We didn't know what was the force of attraction. We do not know the laws of attraction. We do not know the expression for energy. We do not know the expression for angular momentum, which is used now to derive Kepler's laws. Newton's laws were born 300 years after Kepler's laws were born. How many years after?
300.
After Kepler's laws were born. Matlab, Kepler did not know the theory of anything. Centripetal force, why planets are going around, nothing. He only observed the position of the planets over the years. Right? He plotted that, and he realized that it's an elliptical orbit. दूसरी बात ध्यान से सुनिए. You will know how much of a killer instinct these people had to achieve that position. So many years down the lane, 500, 600 years down the lane, even now it is a mystery for us regarding the precision with which they were. 15th century, what kind of telescopes do you people they might have had? Very
So they didn't
primitive,
have
right?
telescope.
Simple
Very
telescope.
primitive.
It came
Yes, sir.
100 years.
Yes, sir. It was invented by
Galileo.
Hans Lippershey, sir.
Precisely a very primitive telescope they had, right? 15th century, they wouldn't have had telescopes which are as sophisticated as the present times.
Yes, sir.
With those primitive telescopes, you cannot observe Uranus, Jupiter, Saturn, none. You had to observe Mercury, Venus, Mars. Right? Far off planets, you won't have observed clearly. Now the other side of the coin. Except for Mars, Mercury, Venus and Earth are close to circular orbits. They are close to circular orbits, very little distortion. Eccentricity for Mercury, Venus are hardly 0.027. Eccentricity is 0, it will be a circle. Conics started for you people?
Yes.
Yes, sir.
We know this.
Eccentricity is 0 for a circle. Venus, I think eccentricity is 0.027. Your naked eye cannot even make out the difference between the circular and elliptical orbit there. Mars also not that great in elliptical orbit. It is close to circular orbit. But Kepler first observed the orbit of Mars more than once. and accurately predicted that this is not in a circular orbit, it's an elliptical orbit. 100 years from then, in 1611, if I am right, they concluded confidently that all planets go in an elliptical orbit. Here, primitive telescopes, you don't even know the theory of these gravitation laws. You do not know how to conserve angular momentum. And you're giving us results with so much of a precision. Confidently, you're telling us every planet goes around the sun in an elliptical orbit, which sun has one of its foci. You observed only Mars. Then you observed the other planets. And by default, if you would have observed carefully planets which are far off, they are more elliptical, it makes sense. Those planets, to my knowledge, with your telescopes, you won't have observed them. And even if you would have observed, you can observe it only for some span of an year. And they extrapolated that and confidently predicted. Matlab, how many years of work they have given, lifetime of a dedication just to spot the position of the planet without knowing any theory. 90% of the discoveries and inventions go with people with these instincts. Every story that you read regarding discovery or invention of really great things, some of the greatest of the inventions are done from the simplest of the thoughts. Thought behind was quite easy. He just plotted the position. Every night he might have spent for years and years plotting the position of the planet. And then he predicted it is an elliptical orbit. See the extent to which it goes. You are drawing an elliptical orbit this way, but Mercury, Venus, Earth, Mars, all of them are close to circular orbit. You are making the diagram more elliptical. First law, first of all, write down the statement of first law. I'll explain. First of all, write down the statement. Every planet goes around the sun. Every planet goes around the sun in an elliptical orbit. Every planet goes around the sun in an elliptical orbit with sun as one of its foci. Every planet goes around the sun in an elliptical orbit with sun as one of its foci. Now listen. This will be the closest distance of approach. This will be the farthest distance of approach. This will be perihelion. This will be apogean. I think in mathematics you call it perigee and apogee. Right? Perihelion and apogean. These are the only two places where angle between R and B will be 90. Anywhere else, R and B will not be 90. This is B and this is R. At closest and the farthest distance of approach, angle between R and velocity will be 90. Second, please concentrate on this. Every problem in this category will be solved using two equations: conservation of total mechanical energy, conservation of angular momentum. Conservation of total mechanical energy and conservation of angular momentum. See the first equation. I am writing between these two. Half m v1 square minus g capital M small m by r1. This is capital M, this is small m. Potential energy, kinetic energy. half m v2 square minus g capital M small m by r. Total mechanical energy is conserved. What is the second equation? Conservation of angular momentum about the sun. Why? Because torque about that will be zero. Force of attraction between the two is passing through the sun. So I can conserve angular momentum about the center of the sun. M V1 R1 sin 90 at perihelion is M V2 R2 sin 90 at aphelion. Sin 90 comes only for these two. Any other place you take, you will have to take sin theta. You are dealing with perihelion and aphelion now. Other than these two, there is no physics involved in this subtopic. Conservation of energy, conservation of angular momentum. What is the only other equations that come? That is pure mathematics. R1 is A into 1 minus E. R2 is A into 1 plus E. What is E called as?
Eccentricity.
What is A called as?
Semi-major axis.
Semi-major.
Semi-major axis. मतलब R1 plus R2 by 2. What if E is equal to 0? It will be a circle. E is less than 1, greater than 0, it will be an ellipse. Did I spell ellipse correctly?
Yes, sir.
Pardon?
Yes, sir.
Equal to 1 will be
Parabola.
parabola. E is greater than 1.
Hyperbola.
Parabola. E is equal to infinity. Straight lines. We will see all the paths in an orbit, specifically satellites launched from a height. What velocity should I give so that it goes in a circular orbit, elliptical orbit, parabolic path, hyperbolic path, straight line? These conditions will come to your rescue. One more important point. I will skip the simplification of these two equations. I have two variables, V1 and V2. R1 and R2 is known to me. V1 and V2 are the two variables. From these two equations, I should solve for V1 and V2. I will skip the simplification and I will write the answer. It is Gm by A into V1 R1 is equal to V2 R2. V1 R1 is equal to V2 R2, isn't it? If R1 is lesser, V1 will be greater. Can I claim V1 is greater than V2?
Yes, sir.
1 plus E upon 1 minus E. V2 will be root over of Gm by A into 1 minus E upon 1 plus. I remember the answer. How do I remember which is V1, which is V2? V1 will be greater than V2. So this will be V1 and this will be V2. This where from did you get? On simplification of these both equations after substituting R1 and R. Every problem in this subcategory will be solved using conservation of energy and conservation of angular momentum. Take it down till here.
So we have to remember these values.
Basically, remember the concept and expression for V1, V.
Okay, sir.
So how did you find V1 greater than V2?
V1 R1 is equal to V2 R. If R is lesser, V will be greater between these 2 points.
Okay, thank you, sir.
The further this amount of high quality data, and he needed to find the best explanation for the motions of Mars, a very tricky problem. There were 3 models of the solar system out there at the time, but none of them worked very well for Mars. First, the Ptolemaic system put the Earth at the center, with the Sun and planets orbiting it in perfect circles. There was also Copernicus's heliocentric model, which set the Earth among the planets revolving around the Sun. And finally, Tycho had his own system to propose, which combined aspects of both. He put the Earth at the center with the Sun and Moon orbiting it, but let the other planets orbit the Sun. All 3 systems relied upon circular orbits, because a circle was accepted as an ideal shape. Copernicus, Tycho, and Galileo all believed that planets should travel along circular paths, but the data just didn't fit. Instead, Kepler found that another shape, the ellipse, works a lot better. An ellipse is sort of like a flattened circle, and it has some special properties. You can draw one by taking a loose string, attaching both ends to the paper, and using a pencil to keep the string taut while moving all the way around the perimeter. The result is an ellipse. The length of the string never changed, meaning that the sum of the distances between each endpoint or focus and any point on the ellipse is constant. In Astronomia Nova, Kepler states that Mars travels in an elliptical orbit around the Sun, which is at one of the foci of the orbit. Later on, he expanded this first law to include all of the planets and demonstrated that this shape fit the available observations. The further apart the two foci are, the longer and skinnier the ellipse, and this skinniness parameter is called eccentricity. Comets can have very eccentric orbits, coming in quite close to the Sun before traveling back to the outer reaches of the solar system. On the other hand, in a perfect circle, the two foci would lie right on top of each other, right at the center. The orbits of the planets in our solar system are not very eccentric at all. They're really very close to circular, which is partly why perfectly round orbits seem like a natural thing to expect in the first place. It wasn't easy to abandon a central idea like that, but with his first law of planetary motion, Kepler rejected circular orbits and showed that an ellipse could better explain the observed motions of Mars. Generalized to all planets, it states that the orbit of a planet follows an ellipse with the Sun at one focus.
Can I rub the board?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Now, one thing you are convinced, closer the planet to the Sun, faster will its speed be. Closer the planet to the Sun, faster will its speed be. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Now listen. When you deal with this, I'm going one step back to Earth and its orbits. What applies for Sun and Earth equally applies for Earth and its orbits.
Yes, sir.
This is Earth. Listen carefully. From a height of h, I am projecting a body with a velocity v perpendicular to r. Right? Perpendicular to r. Listen and concentrate on this. Stop typing messages. I'm not reading any. This is the velocity which is perpendicular to r. If the velocity is perpendicular to r, there are three things that can happen. That should be a circular orbit, or it should either be the closest distance of approach or farthest distance of approach. Agreed?
Yes, sir.
Yes.
So if I give equal to orbital velocity, this will go about in a circle. I wish I have drawn a proper circle. If I project it with orbital velocity, it will go in the form of a circle. Yes or no?
Yes, sir.
Yes, sir.
Now, what if I project it perpendicularly but with a velocity v lesser than the orbital velocity?
It will swirl back to the planet.
Have a look at this orbit. It is a bound orbit. It will go about in an elliptical orbit. But the beauty is, this will be the farthest point for this elliptical orbit. Why? Because velocity is lesser. Recollect what we did right now. In an elliptical orbit, this was the Sun. Farther the distance, lesser the velocity. R is greater, velocity is lesser. Now you decrease in the velocity. So this should be the farthest point for this elliptical orbit. Do you get this point clear?
Yes, sir.
Yes, sir.
Can you please repeat
It
this
has
once
to be
again?
one among the three. Either circular orbit, closest distance of approach, or the farthest distance of approach, right? It
Yes,
cannot be a circular orbit because velocity is less than orbital velocity. So now either this point is the closest or the farthest. Because velocity is lesser, I will claim that is the farthest distance of approach from the focus of this elliptical orbit. Third option, I will increase the velocity now.
Parabola.
जिसने भी पैराबोला बोला ना, अगर तू मेरा सामने होता था तो आज तेरा बैंड बजा दिया होता। Velocity is greater than orbital velocity but lesser than escape velocity. Velocity is greater than orbital velocity but lesser than escape velocity. It doesn't escape. It is in bound orbit. It is in an elliptical bound orbit. Now, this point, velocity is greater, r will be lesser. Velocity is greater, r will be lesser. For this elliptical orbit, can I claim this is the closest distance of approach?
Yes, sir.
Yes, sir.
It has to be. You have only three options. Either circular orbit, or the farthest distance of approach, or the closest distance of approach. When velocity is lesser, it will be at the farthest distance of approach. Here velocity was lesser. This point is at the farthest distance of approach. Here velocity is greater. This point is at the closest distance of approach for this orbit. Agreed?
Yes, sir.
Job not yet done. Please concentrate. If I give it equal to escape velocity, you are aware of the fact escape velocity is √2 times orbital velocity, right? So here the velocity is greater than orbital velocity but lesser than escape velocity. If I give equal to escape velocity, it will be a parabola. Greater than escape velocity, it will be a hyperbola. Equal to infinity, it will be a straight line. We have used Kepler's laws to understand the path of a satellite. Without doing the mathematical calculation, we could predict what will be the path of the satellites. Take it down till here.
Sir, how did we prove that for v equal to escape velocity it will be a parabola, and for v greater than escape velocity it will be a hyperbola?
V is equal to an escape velocity. It will escape from Earth's gravity.
So, but why can't it be a hyperbola rather than a parabola?
That mathematical calculations we'll do at the end when the revision lectures are going on. But you are able to visualize that, right?
Yes, sir.
Mathematically, to prove that this will be a parabola only, we'll do it in the last while dealing with the revision lectures. We don't need that because JEE people prescribe Kepler's laws and in brackets they wrote circular orbits only.
Sir, in all cases, the velocity is perpendicular to the radius, right?
Hence, whole of the analysis. When it is perpendicular, only then there will be three options: circular, closest distance of approach, or farthest distance of approach.
So, sir, when light passes closer to the Earth, it is bent in a hyperbolic path.
Light kahan se?
From the sun, for example.
From the sun, it comes straight near. But going away from Earth is pulled in.
So it's pulled into an hyperbolic path. Okay, sir.
Mass of the Earth. Orbital velocity. The velocity required for an object to revolve around a planet in a circular orbit is called orbital velocity. It is denoted by v naught. Expression for orbital velocity. Let us consider an object of mass m, satellite, to revolve around a planet Earth of mass m and around radius r. Let m is equal to mass of satellite right above surface of Earth. R is equal to radius of Earth. V naught is equal to orbital velocity. M is equal to mass of the Earth. The force F required by the satellite to keep by r square between the satellite and the Earth. Therefore, mv naught square by r is equal to gmm r plus h, the planet at a height h. Here, r plus h is called the orbital radius. Orbital velocity does not depend upon the mass of the object. It depends on the mass of the planet, radius of the planet, and height of the object from the surface. H is very small when compared to the radius of the planet r, then r plus h becomes r. In such case, therefore, v naught equal to gm by r square by r. The minimum vertical velocity.
He didn't show us the parabola and hyperbola in this. He only concentrated on orbital velocity. It's okay. I'll search and keep that video. Can I rub the board?
Yes, sir.
Homework was given for you people up to which problem of HCV?
26.
26.
Sir, and you gave 3 short examples also.
Yeah. For 1 second, even stay online. Homework need to be given from booklet as well. In chapter exercise, page number 157. In chapter exercise, page 157, booklet. There are 5 problems, 1 to 5.
So there are 6, I think.
Okay, 6, 1 to 6. Then page 163, there are 9 problems. 1 to 9. Exercise 1. Exercise 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. First 14 problems. Exercise 1, 1 to 14. Is the homework clear?
Yes, sir.
Yes, sir.
Next class, almost gravitation will be over. So remaining part will walk into in the next class. Our next class is day after tomorrow, right?
Yes, sir.
Yes, sir.
Right, sir.
So finish off this little bit of a homework before day after tomorrow.
Okay. Sir, will you be sending the recording of this class or is it on the YouTube channel already?
Why do you need the recording of
Sir,
this?
I missed one part of the writing part, so I'll just go back and refer to that and finish it in my notes.
Okay, I'll send it in the group.
Okay, sir. Thank you.
Sir, I had a doubt,
Hello.
but
Thank you, sir. Bye,
it is
sir.
like not related to the chapter theory, but related to gravitation. So should I ask it now or later?
Hello.
So the Cassini missions had Venus flybys, but we consider gravity to be a conservative force. And what was the need for the flybys?
I didn't get your doubt.
So like the Cassini missions going to Saturn, went to Venus and had a slingshot like flybys there
Yes, sir.
around
Sir,
Venus. But gravity is a conservative force, right? So the work done won't be like stored in the satellite somewhere. So like what was the
Problem for the satellite is you are turning it. See, you're standing on a surface with friction. Turning is quite easy. Without friction, turning will be consuming enormous energy. At the same time, you're turning the satellite to make it fire in one particular direction. That will come in the next class only. Wait for the next class.
Hello, sir.
Huh.
So for V less than V naught, how did we decide ki is the ellipse with the perihelion? Like by seeing we get the feeling, but it can be that the other end it goes and
Mathematically, that proof we will do it while dealing with the revision lectures of it. Right now, we are giving you a feel of the object.
so for now we just take the feel, right? No need to.
Because you don't have anything beyond this in the syllabus. That's the problem.
Okay,
We don't
sir.
sit and prove these mathematical parts.
Okay, thank you, sir.
See you people in day after tomorrow's class. Good day. Bye.
Thank you, sir.